Welcome back, everyone. We are to section 7.4, where we are going to be doing partial fraction decomposition. That's quite a mouthful there, and this section is quite dense. There's a lot going on in here, and most of it is algebra. So the calculus part of it is actually the easy part. So I'm going to be doing some refresher algebra lessons as a part of this. So if we start here, and we notice that we have two different denominators, and to combine them up, we need to get a common denominator, which will bring us to here. And you can see this is this. But what we want to do is we want to go from this direction back to here. So we're going to be going backwards because as you can see, to integrate that, that's not particularly easy to do. But to integrate that, that's literally one step. So if we do want to integrate that, we can break it down to here, and you'll notice it very easily. We can just natural log it as our answer. So we're going to talk about how to do that. We're going to start out with one particular trick, this first case, and we're going to be talking about rational equations. And the first thing we need to keep in mind is if we have a rational equation and then the numerator degree is larger or equal to the denominator degree, we have to perform long division. So I'm going to go off to the side here. And I'm going to divide this out. So x. Just be real careful. That's x minus minus, right? So that's just 2x. And it's going to be plus 2. So it gives me a remainder of 2. So actually this integral here becomes the integral of x plus 2 plus 2 over x minus 1 dx. Which makes it very, very easy to integrate now that we've done that. The x just becomes 1/2 x squared plus 2x plus, and that's going to be 2 ln of the absolute value of x minus 1. Now, to be clear, if there was a coefficient on that 2, we would need to, or on that x, pardon me, then we would need to take that into account with the integration. That's our constant. All right. So, by the way, we have to always check for this. Again, if the degree is larger than on top, or if it's the same, we still have to do long division. And we'll run into an example where they're the same as well. All right, now we are to case 2. Now, if the degree in the numerator is less than that of the denominator, like we have here, then what we can try to do is factor the denominator and come up with a way to algebraically break it up like we were talking about up here. So off to the side, I'm going to come here, 2x cubed plus 3x squared minus 2x. And I'm going to factor that. That becomes x times 2x minus 1 and x plus 2. So here's what I'm going to assume. I'm going to assume that, let me grab a separate sheet here because we're going to run out of space here. I'm going to assume, and this is just the algebra part of it so far, x squared plus 2x minus 1 over, and I'm going to write its factored form, x over 2x minus 1, x plus 2. I'm going to assume that this can be broken up into a over x plus b over 2x minus 1. By the way, when we integrate that, we got to be careful of that extra 2 there, plus c over x plus 2. So I'll come back to the integral here in a second, but I want to work on this algebra just a little bit. And what I'm going to do is, what we want to find out is what A, B, and C are, because then we can do a nice easy integration with that. I'm going to actually multiply this through by the LCD. And we're going to get x squared plus 2x minus 1. And you can see here the x's are going to cancel out, so I'm going to be left with a times 2x minus 1 times x plus 2 plus b times x plus 2 plus c times x times 2x minus 1. Now you'll notice each of these denominators get dropped out, and you can see we're going to have quite a mess here on the right-hand side. So I'm going to FOIL here and distribute the a, distribute. And what I'm going to be looking for is the coefficient of the x squareds, the coefficients of the x's, and the coefficients of the constants. So let's do this. So this becomes, I'm going to cheat just for a second, look down here, 2x squared, 2ax squared plus 3ax minus 2a, that's a minus 2a, plus bx squared plus 2bx plus 2cx squared minus cx. Okay, so we've gotten through all of that, and what I need to do is I'm going to need to go through and gather all the x squared terms together, gather all of the x, the first power terms together, and then finally the one that doesn't have an x at all. And I'm going to rewrite it like this. So I'm going to take the 2a plus b plus 2c, and all of those have the x squareds associated with them. So let's associate that with the purple. Next up, we have just the x terms. So let's make those blue. And that is going to give me 3a plus 2b minus cx. And finally, we have minus 2a. And I want to associate this with the purple and this with the blue. And I will take this and associate it with the red. And what we're going to do is we're going to create a system of equations. So 2a plus b plus 2c is going to equal the coefficient here in front of its x squared. That's going to be a 1. Next up, 3a plus 2b minus c. That's going to be equal to 2. And the negative 2a is going to equal negative 1. And I'm going to show you a rapid way to do that with a graphing calculator. So I'm going to go to matrix, and I'm going to edit my matrix, and it needs to be 3 rows by 4 columns, the A's, the B's, the C's, and then the equals. So I'm going to put these coefficients in here. After I load that up, I'm going to quit out of that. And I'm going to do what's called reduced row echelon form. That's going to show up as RREF. Here's how we find that. I'm going to go to matrix again, math, and I'm going to scroll down. RREF, reduced row echelon form, also known as Gaussian Jordan form. And I want to do that to this matrix, which was matrix A, second matrix, matrix A. And I'm going to get even fancier, and I'm going to convert these answers to fractions. So convert to a fraction. That was math, and then convert to a fraction. Here we go. There we have it. So this means that A equals 1/2, B equals 1/5, and C equals -1/10. Which means, so I can fit it all in the same thing, I can now rewrite this, my integral, as 1/2 times the integral of that, plus 1/5 times the integral of that, minus 1/10 times the integral of that. So I'm going to do that down here. So this gets rewritten as 1/2 the integral of 1/x dx plus 1/5 the integral of 1/2x minus 1 dx minus 1/10 the integral of 1/x plus 2 dx. All right, and again, I'm getting those from my solutions here. So now I can integrate this. I got to be careful with that extra 2 there as I integrate that. So this becomes 1/2 ln absolute value of x plus I'm going to get an extra 1/2 when I do a substitution there. So this becomes 1/10 ln of absolute value of 2x minus 1 minus 1/10 ln absolute value of x plus 2 plus c. It's a little crooked there, but you get the idea. Now, this is the process when we have what are called distinct linear factors. These are distinct, meaning I'm not repeating any of them. And that's how you would get that. Once again, that 1/5 became a 1/10 because of that extra 2 there. So when I do a u substitution and u becomes the denominator, I get an extra 1/2 in there. That's where that 1/10 comes from. All right, let's step it up to the next. What if we do have repeated factors? So you have a big space up here. That's going to be for my, again, long division. You can see the numerator exponent is larger than the denominator exponent. So I'm going to start with long division for number 3 here. So that's going to be x cubed minus x squared minus x plus 1. And I'm going to notice up here that the x cubed in the numerator is missing. So I'm going to fill it in just as a placeholder there. If you're wondering if we need to do this, the answer is yes, we do need to do this part of it. Okay, so I need x. X gives me x to the 4th minus x cubed minus x squared plus x. X to the 4th minus x to the 4th is 0. Now be careful here, this becomes 0x cubed minus minus, this becomes x cubed. Again, negative 2x squared plus x squared is minus x squared. 4x minus x is 3x. Then bring down the 1. We will start again. I now need something times x cubed to give me x cubed. That's going to be plus 1. So x cubed minus x squared minus x plus 1, and then subtract. gone, 2x. Pardon me, 4x, right? 3x minus minus, so it becomes plus. And that's it. So this gets rewritten, this integral down here gets rewritten as, and you know what? I'm gonna grab my sketch paper again. I'm gonna go ahead and factor that denominator as well. I'm gonna factor by grouping. And I can further factor that as the difference of squares. There we have it. So this is now all going to become the integral of x plus 1 here, plus 4x over, and I'm going to rewrite the denominator in its factored form here. Notice I have a repeated factor there. All right, I am now going to focus on breaking this down. Now, a couple things I want to point out before we get started on that part of it is that if I have this here, and I want to combine them all up, what's my common denominator? It's this. However, if I do this as a separate problem, please note that the LCD for both of these is that. So we don't know if this is going to be included as part of this breakdown or not, just by looking at the LCD, because this LCD matches both. So we're going to assume that that's going to be there. Now, if it turns out to be where there's no single term like that, then that, whatever that number is, or letter is, will become a 0. So it'll be gone anyway, and it'll be our regular one. So when we have a repeated root, we have to include all of the degrees down from that we would have. So I'm going to take 4x over x minus 1 squared x plus 1. And I'm going to assume that this can break down as a over x minus 1 plus b over x minus 1 squared. So we're going to assume that that one's going to be there. If it doesn't, then that a will be a 0 plus c over x plus 1. And now we're going to do that same thing that we did before. We're going to multiply through by the LCD, and we'll set up a matrix. All right, so that gives us 4x over here equals a times x minus 1, x plus 1, plus b times x plus 1, plus c times x minus 1 squared. So now we're going to FOIL and distribute. And by the way, I want to rewrite this 4x like this. 0x squared plus 4x plus 0. And that will matter here in just a moment. So let's FOIL it all together. This becomes ax squared minus a plus bx plus b plus cx squared minus 2cx plus c. Right. Again, this lesson's very algebra heavy, as you can see. I'm going to go ahead and rearrange it so that I get my x squareds together, I get my x terms together, and I get my non-x terms together. So a plus c x squared plus b minus 2c x plus negative a plus b plus c. And now we're going to match it all up. So a plus c equals 0, b minus 2c equals 4, and negative a plus b plus c equals 0. So we're going to do reduced row echelon form again. Again, this is going to be a 3 by 4. And I'm going to reuse matrix A, why not? Now, whatever's missing, we've got to fill in with a 0. So it's going to be 1, 0, 1, 0, 0, 1, negative 2, 4. And then here I have negative 1, 1, 1, 0. And let's see what we get. So I quit out of that. Now I'm going to find reduced row echelon form, and I'm going to go ahead and convert them to fractions again. And if they're not fractions, it will just reduce it to a nice integer. Math, reduced row echelon. And that is matrix A. And convert to a fraction. Math, fraction, go. There it is. So A is 1, B is 2, C is negative 1. Which means I can now, and by the way, just to be consistent, this becomes 1/2 x squared plus x. So I integrated those two there. Plus A was 1, and to be clear that A was over the x minus 1. So the integral 1 over x minus 1 dx plus 2 times the integral of 1 over x minus 1 squared dx minus 1, the integral of 1 over x plus 1 dx. And we already have a plus constant there. All right. Here we go. Now this is going to become a negative 2 over 1 over x minus 1. And then minus ln absolute value of x plus 1 plus c. Now I'll clean that up in just a moment. I want to show you what I did with this one here. So the integral of 1 over x minus 1 squared dx. I let u be x minus 1. So du is dx, no problem. And I did the 1 over negative 2 plus 1. This is the power rule, right? U to the negative 2 plus 1. And that becomes negative 1 over u, which is negative 1 over x minus 1. So that's where the negative came from, and the 1 over x minus 1 comes from. And so our final answer is there. That was a lot of work, but you can see the calculus part of this is really easy. That's not the stress here. So we started with long division because the degree on top was larger. We broke it up. These two integrations are very simple. And then we did this entire process with repeated, I have to do all. So if this was x minus 1 to the third power, I would need a second power and a first power. So I would need all of those. So I would have an A, B, C, and D in that case. And then do the integrals for that. That one is messy. So for example 4 down here, you can see I don't have a lot of room. I'm not going to finish 4. I just want to set it up for you as far as the partial fraction decomposition goes. So x squared plus x plus 1 over x plus 1 squared x plus 2. And so this is going to become a over x plus 1 plus b over x plus 1 squared plus c over x plus 2. And you can see this is very similar to what we just did. This one is a definite integral, and I'm going to leave that for you to try. This video is already going to be way too long. So next up, what if we have a non-factorable quadratic, like we would have here? Well, if we have a non-factorable quadratic, then on top of it, instead of a constant like a or b or c, we're going to need a potential linear equation up top. So here's how we're going to handle that. This is going to become a over x minus 2 plus bx plus c, so there's my linear, over my unfactorable quadratic. And same for this one, dx plus e over x squared plus 4. Now, fortunately, we're not going to, to actually work this one out. You can see we're going to have a massive matrix. It's going to be a 5 by 6, actually. But it's workable. It's just a lot of algebra, and I don't want to waste time doing that. A quick rule to keep in mind, I derived this in another video, that the integral of 1 over x squared plus a squared is going to be 1 over a inverse tangent of x over a plus my constant. We're going to need that for this next one, probably. All right, example 5. I'm going to notice that the degree in the numerator is smaller than the degree in the denominator, so I don't need to do any long division, but you always need to check for that. I'm going to factor this denominator, and in fact, I'm going to do that on a separate sheet of paper. We'll do the partial fraction decomposition part of that here. So let's factor that. Okay, it's a 4. So we're going to assume that this is equal to a constant over x plus, and because I have a non-factorable quadratic, I'm going to have a bx plus c down here. And we're going to break this open by multiplying through by the LCD. Equals a times x squared plus 4 plus bx plus c times x. And now I'm going to rearrange these so that I get the x squareds together, the x's together, and the constants together. That is going to match up quite nicely. So a plus b equals 2. C equals -1, very nice. for a equals 4. That's nice. That means that, here's one of mine. This means that a is 1. Plugging that into here, 1 plus b equals 2, which means b equals 1. All right, so I'm going to rewrite this here as the integral of a is 1, b is 1, and c is -1. So here we go. This becomes a, which was 1, the integral of 1 over x dx, plus b is also 1. So that's going to be the integral of 1x minus 1 over x squared plus 4 dx. So that's nice to break it down like that. All right. This first one's easy. That's ln absolute value of x. Plus, I'm going to break this up. Like that. All right. I'm going to do a quick substitution here. Now I'm dealing with each of these separately. This one, I'm going to use this rule actually in just a minute, where a is 2. So technically I get 1/2 du equals x dx, and there's my x dx. Let's see. Plus 1/2 the integral of 1 over u du minus, and now I'm going to use this rule here where a is 2. So that's minus 1/2 inverse tangent. That's the 1 over a, the 2. Inverse tangent of a over x. So a over 2, I'm sorry, x over 2. And so in this case, that's going to be x squared plus 4 over 2 plus c. All right, we end up with natural log absolute value of x plus 1/2 ln absolute value x squared plus 4. Absolute values are unnecessary there because that's always positive. Minus 1/2 inverse tangent of x squared plus 4 over 2 plus c. All right. We are moving on. This should just be x. What am I doing? That's just x. That's just x over 2. Let me rewrite that last part. Negative 1/2 inverse tangent x over 2 plus c. These two are the same. Sorry about that. This last one of the repeated root is just like the previous one that we just did. But what I want to do is just set it up for you like I did that other one. Over x plus bx plus c over x squared plus 3. And I'll let you crank that one out. All right. For this one, what we're going to do is we are going to complete the square. So I'm grab my scratch paper. X squared plus 2x plus 5. X squared plus 2x plus 1 minus 1 plus 5. And that is a perfect square. If you're wondering where I got the 1 from, I took the 2, cut it in half, and squared it. That gives me a 1. And also, I can let u be the x plus 1. So let's break that down. All right, so I'm going to let u equal x plus 1, which implies, by the way, that x is equal to u minus 1. When I plug that into here, I get the integral. Now, when I plug in x to here, that's going to be u minus 1 plus 4, so that's u plus 3 over u squared plus 4. Again, that's this here, u squared plus 4 du. And this once again gets broken up. U squared, pardon me, plus 4 du plus 3 times the integral of 1 over u squared plus 4 du. And we've already done similar integrals here. So this one becomes the 1/2 ln absolute value of u squared plus 4 plus 3, the 3 from there, halves inverse tangent of u over 2 plus c. I'm replacing u back with the x plus 1. We get absolute value of. So just to be clear, u squared plus 4 is here, is this. So I'm going to go back to the original. So if I FOIL that, combine like terms, I'm going to get back to there. So I'm going to go back to the original problem. This is the x squared plus 2x plus 5 plus 3 halves. This is that inverse tangent trick again. So inverse tangent of u, which is x plus 1, over 2 plus c. All right, we got one more to go. And I'm only going to get you started on this one. First off, I'm going to notice that I have the same degree. So I'm going to have to do long division here. So let's start long. Notice the degrees are the same. So let's switch colors real quick. To get 4x squared from 4x squared, I have to multiply by 1. So 4x squared minus 4x plus 3. Subtract. Those go away. Negative 3x plus 4x just gives me x. And 2 minus 3 is minus 1. So this integral becomes the integral of 1 plus x minus 1 over 4x squared minus 4x plus 3 dx. And I'm going to leave this challenge to you. I'm going to let you work this out. you will need to use nearly every trick that I taught you today as far as algebra goes to deal with that there. Good luck. I hope you found this helpful.